The broadcast is now starting. All attendees are in listen-only mode.
Well, great. Well, hi, everybody, and welcome to the Seattle Use R Meetup group. Thank you all for being here today. We have some great speakers joining us, and Namita and Dani from the Seattle Kraken. We won't be talking explicitly about the stuff they do there, I'm sure, but the way they use R and the cool ways that R can be used in sport. As always, if you have any ideas or any things that you'd like to see us organize a meetup about, please send me or Daniela a message on meetup.com and we can try to make those sorts of things happen, because these sort of meetups are crowdsourced. They're just, we come up with ideas of things that we think you want to see. And so we want to hear from you when you have something that you'd like to see or present. So I think we'll give it another like 2 or 3 minutes to let everyone log in, and then we'll get started with the presentations. So we'll just hang out for a little bit. Oh, also, if you have any questions or comments, feel free to post them into the chat, and at the end of the meetup, we'll address those and pose any questions you have to Dani and Namita. Actually, I'm tired of waiting. Awkward silence isn't great, so we might as well get started. So first up is Namita. Namita, why don't you give some background on yourself and go and get this thing going?
Sure. Yeah, so actually, I'm thinking I'll introduce both of us because I love bragging about Dani as well. But I'll start with myself. So my name is Namita. I'm currently the Senior Quantitative Analyst for the Seattle Kraken, formerly known as NHL Seattle. I've been working for the team since March, and before that, I spent 2 seasons as a quantitative analyst with the Philadelphia Eagles. And I graduated from Wharton with a degree in econ and a concentration in statistics. And yeah, I've just last couple of years doing a lot of hockey and football research. So I'm excited to share some of that today. And then I also do want to intro Dani because he is my partner in crime, and he is a quantitative analyst for the Kraken. So we both work in hockey ops together. He graduated from Simon Fraser with a master's in statistics, and he has done research in even more sports than I have. So he's done some awesome football research for the Big Data Bowl, which he's going to share after I give this talk. And then he is also been an intern with the NBA League Office. And then he's also doing some great hockey research for us. So yeah, I think one of the things I love about our little team is that we have a lot of different sport knowledge, which is definitely pretty cool. So I hope you guys enjoy both of these presentations, and yeah, we look forward to giving them. So with that said, I'm going to jump right into my talk. So the title is Finding Expected and Unexpected Goals with R. And this is the only thing I've adapted from when I gave it in January, just because I feel like having this context is really, really important. So this presentation was given at the end of January, which is one of my last weeks with the Eagles, which is why it's about hockey, a sport I technically no longer have any public opinions on. You know, another fun part of that conference was Dani and I knew that I would be signing with NHL Seattle very shortly, but we had to pretend like we didn't know that, so it kind of felt like spies a little bit. But we're the Kraken now. We got named that last week, and it's awesome. So just something to keep in mind that, you know, this is all stuff that I did before I joined the team, and it's all stuff based on public data. So yeah. I find that especially when I'm giving presentations to nerds, I sometimes have to contextualize the sports a little bit. So I found that the best way to describe and explain hockey in the most concise manner possible is that it's violent soccer on ice. And 31, soon to be 32 teams in the NHL spend all year trying to be good enough at this, they win the Stanley Cup. Why does it matter? Some people, such as us, think it's fun. I love that GIF from Arrested Development. But also, you know, I just want to make the point that, you know, I think both Dani and I just started analyzing sports because we were big sports fans, and we thought this could be a cool way to apply the stuff that we were learning. And then, you know, we're fortunate enough to be able to do it for our day job, which is really awesome. So getting right into evaluating hockey, you know, some ways to evaluate teams and players. So certainly the goal at the end of the day is to win as many games as possible. So you could look at your win percentage. In order to win, you got to score more goals than the other team. So you can look at goals for versus goals against. In order to score goals, you got to take some shots. So you could look at shots for and shots against. Or, and I always like to mention this, you could just rely on your feelings. And that's also very valid for all you hockey fans out there. But for analytical purposes, shots have a very interesting and nice property of being one of the most granular things we can observe. So while you might see, you know, a handful of goals per game, you're going to see dozens of shots per game. So that feels more compelling from a statistical point of view in terms of the data we can use. But people do say that, hey, not all shots are equally dangerous, and they're right. So then the question becomes, what other features can we account for? So let's take a look. And this is a goal from the most recent regular season. And this is where some more context is also necessary. So before I joined the Kraken, I was a Philadelphia Flyers fan for about 10 years, which is why I chose this goal from them. And yeah, we got this nice slowed down GIF via the Flyers. Hopefully that's not rendering too terribly, but you know, I'll explain some details about this as well. And the nice thing about that goal is that those, you know, videos, those GIFs are not the only information that we have about them. The NHL also releases play-by-play data publicly that gives us some additional context. So we know, for example, that that was a shot that became a goal. We know that it was scored by Flyers forward Travis Konecny on Kings goalie Jack Campbell. We know that it was at even strength, so there's 5 skaters on each side. We know that it was right in front of the net, about 18 feet away. So, you know, I've kind of shown the precise location that they've marked the shot at in that little rink there. We know that it was a wrist shot, and we know that it caused the Flyers to go up 2-0. There's also some stuff that we don't know from the play-by-play data. And, you know, first and foremost, I did notice that just based on watching the play, it did seem like Konecny was a bit further left, I guess I would say, or actually a bit further right, sorry. So anyway, I marked the actual location where I might have labeled the shot. And, you know, I might not be perfectly right either, but you know, one of the things to keep in mind is that all of these shots are manually tracked. So it's just someone, you know, in the stadium looking at the shot and being like, I think it happened from here. And so there's some error and some bias that can creep in from that perspective. The other thing that we don't know from the play-by-play is that James Van Riemsdyk set up Travis Konecny really well with a great quick pass. We can't see from the play-by-play that he was wide open. And we also can't see that there were 2 players screening the net. So all of this is to say that, you know, we do have some helpful contextual information, but there's some missing from the public data. And I would say that most of these features that are missing would probably lend themselves to suggest that the shot was, you know, more dangerous than you would think if all you knew was that kind of basic play-by-play information. In general, we know that 5v5 unblocked shots go in, become goals roughly 6% of the time in the 2019-20 regular season. But I think, you know, Travis Konecny's shot was a bit better than that, both from the information that we saw in the play-by-play and from the information that we didn't see. But the question is, you know, what should we do about that? And this is where I finally get to say the phrase expected goals. So I think, you know, just based on thinking about all the features of shots, I think hopefully many of us would agree that it does seem like a worthwhile endeavor to contextualize shots with all of this additional information that we have and really turn them into an estimate of the probability of scoring. So instead of saying, you know, this is one shot, we can say this is a shot with a 6% or a 10% or a 15% chance of scoring. And then if you add all of that up, you can get an expected goals total. And I think something that I want everyone to come away from this with is the idea that everyone with a passable understanding of hockey, which I will say that I've already given you with my violent soccer on ice definition, and R, can build an expected goals model right now. And then, I personally think that this is a fun way to spend my time. That's probably why I'm in the job that I am, but you guys can decide that for yourselves. I would be remiss to mention expected goals without talking about all the people who came before me who have looked into this, some of them many years ago. So these are all really great people to look up and resources to look at. I would say in particular, the ideas about the model building are not really particularly brand new or mine, but I do hope that I present them in some fun ways. And we can go right into talking about the data source. So I'm using, again, publicly available data from moneypuck.com. So Peter Tanner scrapes NHL data every day and shares season level CSVs of every unblocked shot. We're going to look at 2017 to present, so the last 3 seasons. And he did some stuff that I didn't feel like doing when I was just doing this research project on my own, so I'm very happy that he did that, and that includes labeling rush shots, rebounds, and more, adjusting XY coordinates for recording bias. So this goes along with what I was mentioning earlier about how all the shots are manually labeled. So there's bias that can creep into that, and there's adjustments that can be made. And he also cleaned it up so that it's very ready to be very tidily analyzed, which is always appealing. And this is, I think, the only slide that has a direct code screenshot on it, and that's because I really, really wanted to emphasize, how simple it is to get started with this data. And I actually even overcomplicated it slightly by trying to, remotely download the file from R. You could just go to his website, download it, and then do a read CSV, and you're in. But I made a function to kind of unzip those zip files and then put it all together. So this is where I really, really encourage all of you, if you're at all interested in this stuff, don't be scared off by the idea that it must be really hard to get, sports data or something. It's actually pretty easy, and a lot of people have done a lot of work to make it easier for people to get started with this data in terms of cleaning it and shaping it and so on. I thought the first thing that would be fun to do would be to make some heat maps. So I just kept it simple, made a map of all of the unblocked shots and where they're coming from, and then made a heat map of the shots that became goals. So right away you can see that these look different, and the especially thing that I want to point out here is that if these heat maps looked exactly the same, then that would imply that every shot is equally dangerous. But already we can see that goals are more concentrated near the net than all shots are. So this, even these pictures sort of justify the need for coming up with some sort of expected goals model. I think, whenever you can start with a logistic or linear regression, you should always do that. So that's what I've done here. I would say that, it's pretty straightforward to think that the most important feature, if we're just looking at one of them, is probably just distance to the net. We saw those heat maps before. So here I'm expecting the probability of the shot becoming a goal based solely on the shot's absolute distance to the net. And just a simple GLM. And so that'll be kind of our baseline model to make some comparisons. Slightly less lazy, but potentially, we don't know if it's better or not yet. We can also try XGBoost, a little bit of machine learning. I think, the biggest justification here would be that we can certainly incorporate more variables, although we could have done that with the regression, but especially we can decide not to assume linearity. So we can try to see if there's, you know, a lot of interactions between these variables that, you know, can help us contextualize things better. So as I mentioned, we're also including more variables such as shot angle, shot type, and time/distance from the last event. We can use XGBoost so as to not assume linearity, as I said, do some cross-validation to choose how far we take this algorithm. And then, you know, just because you're always supposed to do this with machine learning, I've put in some Google image results with like big brains and stuff to make this seem a lot smarter than it has to be. But yeah. Just a quick note on some other variables. I decided not to include score state. So that would be like whether the team who was shooting was like down 1 or up 1 or something. It didn't really seem like a super important variable to me at the time. And then the other thing is that I decided not to incorporate specific parameters for shooters and goalies. You know, so if you really wanted to add information to the model by saying, this is the specific person who shot this is the goalie that they were facing, you certainly could do that. But another way to evaluate them would be just to be by looking at their residuals. So comparing their actual results to their expected results, which can be thought of as like sort of the average player expectation. We can look at some XGBoost variable importance metrics. So I think this is generally unsurprising that like definitely the most important variable is shot distance. And then below that, just like the Y distance from the net. So I would say that it does seem like, you know, we probably encompassed a lot of the information just by looking at, you know, shot distance in the logistic model. But, you know, shot type is less important, but it does matter a little bit. I do also love using GM Smooth to glance at calibration. So, you know, just fitting the expected goal value versus the actual 1 or 0 result and throwing a smooth on there. And we can see that both the XGBoost model and Money Puck model, so Peter is kind enough to incorporate his own expected goals values in the data set. So that's another nice point of comparison. They seem to be fairly well calibrated, you know, from like the 0 to 30 to 40% mark, and then they kind of shift a little bit, which really is fine because you don't see a lot of shots that have really high expected goals values because frankly goalies save most of the shots that they face. You know, another thing that I would point out is just that by looking at shot distance alone, like the logistic model, you're only really ever going to see values in between 0 to 25%. But once you add some more of those variables, you can start to identify some of the more dangerous shots. Lastly, we can get some real model stats here. So again, we have 3 different points of comparison for the XGBoost model. So if we assume all shots are the same, obviously we're not going to have a particularly great area under the curve and log loss. And also, if you remember that Travis Konechny goal from earlier, like I said, we would just assume that, you know, it's roughly 6%, which we all, I think that it's more dangerous than that. If we just use the logistic model with shot distance, you know, right away we can improve both the log loss and area under the curve substantially. And also, Konechny's goal does look a lot more dangerous. Using XGBoost, we can make a slightly more marginal improvement in both of those metrics, and then also see that TK's goal does become even more dangerous in hindsight. And again, this is the cross-validation results, so we're not actually seeing his goal when we're estimating it. I feel like that's always important to emphasize, but already, you know, this shot looks twice as dangerous as just sort of the quote-unquote average shot in this data set. And then lastly, looking at Peter's model with Money Puck, we can see that it is a marginal improvement over XGBoost, but we've gotten most of the way there, I think, with some relatively simple features and some hyperparameter optimization, although certainly if you spent more time on it, you could probably improve it a little bit. And then the last thing I'll say is that one of the cool features about this is being able to do some evaluation of specific players. So I mentioned, shooters and goalies earlier. One of the things we can do once we have these values of expected goals for every shot that a player takes is we can figure out their expected shooting percentage. We can compare that with their actual shooting percentage and start to identify players that are really good shooters. And one thing I'll say about this is that it's a fairly narrow definition of shooting talent, in that it's really saying that, like, if you had a shot somewhere on the ice and you could make any single shooter take that shot, you would probably want someone with a really high residual. But another aspect of being a good shooter is being able to get to dangerous places on the ice and then shoot the puck from there. So that's something to keep in mind. But yeah, so here we've just looked at every shooter, used the summarize command to figure out their expected and actual shooting percentage, and then sort by that differential, make sure we don't have any low sample players, and we can see, the top 6 players here. I'm not going to talk about my opinions about these players in particular, but what I will say is that when you do make models like these and you look at the top players, you'll see a lot of players that can be thought of as star players that everyone knows, but you also see some players that are maybe lesser known, and that's always useful, especially if you're, let's say, working at an NHL team to try to identify talent and players who are under the radar. So with that, I'd like to thank all of you for listening, and especially thank all of the public analysts who in some way or another contributed to this presentation, and more generally to me just having a really great time doing public hockey research the last couple of years. So that's Money Puck, Manny Perry, Micah Blake McCurdy, also known as Ineffective Math, Evolving Wild, and lots of others. And yeah, you can find me at NNStats on Twitter. But that's all I got.
Great. Thank you very much, Namita. That was very interesting. I enjoyed and learned a lot, and it's exciting to see the different. Can you hear me? The different ways. All right, great. The different ways that that R can be used in different ways. Obviously, I work in a very different field than you all. Next up is Dani. Dani, are you ready for presenting? I'll give you control.
Good to go.
All right, I'm going to make you a presenter. All right, so now you should be able to share your screen and you can get going.
Can you see my screen?
Yes, we can. You can see.
How does that look?
It's loading. All right, putting the fun and functional data. Perfect.
Cool. So just wanted to thank Namita for the wonderful intro on my behalf, and Alice for hosting, and for all of you guys for listening, and Namita for the great presentation before mine. I will also say that we are not the only people who make up our team at NHL Seattle, and that, or I gotta switch it, Seattle Kraken. We're not the only people on our team, and I think it's a really great way of R and a lot of other languages merging together. And that's probably a whole other talk, but there's a lot of other great coworkers that we have there that we're doing work with. So yeah, so my talk is called Putting the Fun and Functional Data and Tidy Pipeline to Identify Routes in NFL Tracking Data. And so this was a project that I worked on with a team of my friends to compete in the NFL Big Data Bowl. So I'll start off by first thanking my collaborators and pointing them out. So Lucas, James, Matt, and I all went to SFU together. Lucas and Matt are also both right now working at a company called Zealous Analytics that does sports analytics research while they finish up their studies, but they have too many titles to fit in a slide. So Big shout out to them, and James does really awesome work and is finishing up his master's very shortly. So just a little bit about me. You guys have heard a bunch now, but I went to Simon Fraser, and I now work at the newly named Seattle Kraken with a fantastic team of analysts and tech folk. So like I said, this is a project we did for the NFL Big Data Bowl. And so this was a competition where they released data to the public, and they released NFL player tracking data. So this is data that's pretty hard to get your hands on. And so it was a really cool initiative that they gave us 6 weeks of data from the 2017 regular season. And what this tracking data is the measurement of each player and the ball 10 times per second on each play. And so you can really see where each player is and how that changes over time. They also give you general gameplay and player level information, and they still have one example file online on their GitHub page. And this is really useful if you want to go play with tracking data and see what it looks like and get experience with that. And so as an example from a play, this is what it does. It's showing you every player on the field, where they went, where they ran, where the ball was, how it was thrown, it was caught, and then it was run into the end zone. Right, so this is the data summarized in a beautiful way, and really kind of shows you what is happening on a given play. And so you saw the lines on that play were drawn, and those are the routes of the receivers. And so we want to come up with a route identification method that will label those routes for us. And so right here is what I've done is I've taken each player that ran the most routes for their team, and I've plotted where they ran on the field in each play. So each different line is a different play, and so you can see that some players have different route patterns than others, and other players have similar route patterns to others. And what we can do is we can cluster them and categorize them by their shape. And so what that looks like is we take each route, we group together the shapes, we label the mean, and then we group those labels together. And so then we can do things like look at all of cluster 20, which are post routes. And so these big blue dots are the mean of that cluster, and each little blue dot is an observation from a route from that cluster. And so you can see that we've kind of labeled and clustered those shapes together. The other thing you can do is you can say how a route develops. So over time, this route starts out as anything, and then as he cuts across the field, it becomes a post route, right? So as he comes down, you can see it's maybe a go, maybe a corner, maybe a post, and as he starts to make the post movement, we can find out that it's a post. So these are the different types of things we can do with tracking data and with route clustering. But that's not what I'm really going to talk about today. I'm going to talk more about kind of the how to deal with tracking data and work with it in R. So we're going to do a little bit more of like R code than Namita showed, where Namita showed you a beautiful kind of works through example of a model. I've kind of showed you what the model output gives us, and I'm going to kind of talk about the code that went behind that. So the three kind of main messages I have are tidy data when it's functional data, and I'll explain that a little bit more. And then two great functions to help you use functional data, which is purrr, map, and purrr safely. So we're going to start with what our data looks like. And so what our data looks like is 91 game files. So each file is a different game, and you can link it to other files by the game ID, the play ID, and the NFL ID. So I have these 91 files in my kind of home directory, and it keeps going on and on for each game. And then when we read in our data, so one of these files, then we get one row per player per 10th of a second. So you can see this example, I'm showing Anthony Sherman, and it's on the first play of the game. It's a kickoff, and if you look at the time, it's happening every 10th of a second. So the time doesn't actually change because we just have seconds here. But if we went to the 12th or 11th row, you would see that it would be 42:00. We also have game ID and play ID that we can join in to learn other things. We have their location in the X and Y column, and their speed and some other information in there. So it's quite a large data frame. You can also see it's 316,000 rows by these 14 columns. So the first thing I'm going to recommend when you're working with these big files, we're going to cut all the information we don't need. So for our purposes, we're going to cut the columns just down to the specific columns that we care about, the join kind of key columns, the X and Y locations, the frame ID, and what team they're from, and what the events are that are happening. Now we're doing the rows. So for our purposes, we only want the passing plays, and we only want the tracking data from players that were running routes on that play. So just from that, we can go from 314,000 rows to 32,000 rows, and now we have a much more manageable data set to work with. And so this is going to be really key when you're working with big data, is to cut everything that you don't need. And so now comes the question about tidy data. So Namita again referenced tidy and tidy analyzing data in her talk, and it's something that's really important and really part of the ethos of kind of working with R. And so what it is this is from the R for Data Science textbook, is each column is a variable and each observation is a row, right? And then, sorry, each observation is a row, and then each kind of entry is a value, okay? And so when we're working with tracking data, I've used this meme, like, is tracking data tidy? We have one observation for every 1/10 of a second per player, but my observational units for, let's say, are actually per player per play, right? So no, it's not tidy data. Each curve is an observation, right? And so this is kind of interesting to wrap your head around. But once you wrap your head around it, it makes it a lot easier to analyze this data. So each observation is a player on a given play, and there's multiple measurements in that observation. Okay, so what I'm going to do is I'm going to tidy up, and I'm going to make a nested data frame so that I have one row per player per play, one row per observational unit. So you can see here on this first play 68 from this game, we have 5 players on the, 5 players on the field that we care about. Each of them ran a route that lasted 87 rows, right? But it's all encapsulated in this tidy data frame. And so then the next play, we have all the players, one row per player per play. Okay, so this is kind of the big epiphany that you have when you're working with tracking data, is that our observational units are actually functions that you need to tidy into a nested data frame. So now we're going to do this for all the files, and so what I'm going to use is a bunch of functions from purrr. So I'm going to take my tracking files, and I'm going to read. I have this read routes from CSV function that's going to do a bunch of tidying. I'm going to read it into a nested data frame. So what this looks like is, now when I have this routes data, I now have 34,000 rows, so 34,000, 35,000 observations, which is 35,000 routes, right? And then each of those routes has observations within them. And so the next thing we're going to learn about is per map. And so what we're going to do is we're going to now work on our observational units that are actually data frames by using maps. So what we do is we pass tracking data into a function called cut plays, and we cut down data even more. We then do some things that modify the data again. We're going to flip the length and flip the width, right? And so what we keep doing is we keep passing this tracking data column to these functions. And so what it's going to do is it's going to operate, it's going to use that function, use our cut plays function on our nested data frame. Okay, and so now we still keep everything as in the observational units. This also makes it really easy to parallelize, which is going to save you time. So this is a really nice way to work with tracking data in the nested data frames by using map and pmap. So pmap just means that you have multiple parameters you're passing in. Okay, and finally we're going to cluster. So now I have again a function that we've written called cluster trajectory data, and it's going to take one row per player per play, and it's going to cluster them all together. Okay, so that's kind of the development cycle. Now I have some tips for how we get to that point. So my last thing is we're going to work with one observation to start, and then we're going to expand to all of our observations. So what I use here is slice. I take our routes data, I slice it, and then I unnest the columns to get one route to work with. And I'm going to work with this. I'm going to build a function off of it. So once I built the function off of it, we can use purrr safely, or so yeah, once I make a function out of it, then I can apply it to everything. So what I've done here is I've sampled 5 random routes, and I'm using a function I've called cut plays with random error. Okay, and what this does is it's going to randomly throw an error, just to illustrate the use case of purrr safely. So right now I'm not using purrr safely, and so what happens is when we encounter an error, we don't know which observation this happened. So if you're writing a function for one observation, then you apply it to all your observations, and you have an error for some reason, you need to figure out where that error occurred. And right now, the way purrr set up, it doesn't tell you. It just says that we could not find the function cut plays. It throws this random error. Okay, so when you use purrr safely, it will return your data frame if everything goes to plan, or what the function is supposed to return if everything goes to plan. And otherwise, this command here is going to return an NA. Okay, and what that means is that after you're done running it on all your files, you can then pluck an error that it throws and save it in the error. You can take your result out and put in your tracking data, and then we can look at which observations had an error and which ones went through properly. So if you want to just throw away any that had an error and just work with the ones that worked, you can just pluck out your tracking data, your results, filter out all the ones that had errors and continue working. Or if you want to explore your errors more, you can look at it closer. So what we have is this is the result of running that purrr safely function. And so we can see here in tracking data, we have a logical 1, which probably means there's an error. Tibble 41 by 4, which means that it worked, and we have an error, and a 32 by 4 tibble that worked. Additionally, in the error column, we can now see that we have sample error, we have null because there was no error, we have error, and a null because there was no error. So this is really clear on which rows your function worked on and which rows it did not work on. And so then what we can do is we can pull out those errors. We want to know where our function went wrong, what happened, so we can we can get the type of the column in the error column. We can filter out all the nulls, right? All the nulls we saw before, and we can see that we are left with a data frame that just has the rows that errored out. So I could go in specifically and look at each one of these rows and see what went wrong, or you can also pull out the errors that happen. And in each of these ones, they couldn't find the function cut plays, which is the random error I made it throw. And so this is really, really super useful for development because now you can investigate the specific observations that went wrong. So the final ton of takeaways is tidy data when it's functional data, and this can happen in sports and outside of sports, using purrr map to work on that functional data, and finally using purrr safely while you're developing to find out where errors are, find out where your problem observations are. So I just want to say thanks again to Ellis for having us on, and thanks to Namita for joining me, and then also again thank you to my great colleagues who helped work on this project with me. If you want more details about the actual clustering, we have a paper in the Journal of Quantitative Analysis in Sports, and these slides should be on my website and on Twitter sometime soon. So thanks everyone for listening, and I think both of us can take questions now.
Great. All right, yeah, Dani, if you want to stop sharing. We can, see the three of us going up. All right. So yes, if you have any questions, go ahead and post them into the questions section there, and I'll read through the ones that we have so far, and you two can alternate who wants to answer or decide if you want to answer it. So the first question that I'm seeing is there a noticeable lift in predicting future team performance instead of using XG instead of just shots? Or can you not answer?
I don't think I can say something incredibly detailed. What I will say is that that may or may not be true, but I think, I think I have presented like a more specific area where, like, even if it wasn't true that XG was predictive in a team sense, it's certainly true that it could help you find like good shooters and stuff. So I think I would just make the general point that like all stats do not have to do all things without actually answering the question.
Yeah.
Do you have anything to add, Dani? Or?
Well, I just think it depends on how you use that to then model. So there's probably another step that you have to take, and it depends on how you model. And there's a lot of public analysts who are doing that. So and validating the results and showing log losses afterwards. So
cool. Is there a statistic in hockey like EPA in football that evaluates each player's value added when on the ice? Y'all are asking great questions, but there's also a question of how much can be shared.
Right. I think again, I would just default to there's a lot of public analysts trying to do that work, and I would point to.
Yeah, I think we can point to some specific websites and analysts that you could go and see sort of the public answer to that. So I mentioned them before, but like I said, I think at Ineffective Math, like Micah Blake McCurdy has been doing that sort of thing for a while. At Evolving Wild, they have a website called Evolving Hockey. Money Puck.
Hockey graphs.
Hockey graphs. Yeah. So, we're going to kind of plead the fifth on that. But if you go to those websites, you will see a ton of stuff on evaluating teams, evaluating players, and so on.
Awesome. Thank you. So here's a non-hockey question. So you can probably answer this one. What's the best way to learn efficient function creation and use? I always have problems when using R.
Right. I think it takes time. And so kind of learning efficient in what way, I think is my follow-up. But efficient in terms of memory, efficient in terms of time. It just takes kind of getting to know the tools, and you're gonna, the first time you go about it, it's not going to be the most efficient way, but you're going to try to get it right. And then afterward, you can kind of look at making things more efficient. But I don't know, that's a great answer, but I think that's part of development, is you try to get the right answer, and then you just try to make it better slowly, iteration by iteration.
We can also just highlight some of the stuff that Dani talked about that I think is definitely important. So, I will say that I've also worked extensively with NFL tracking data, although I don't have anything to share about it. But Dani made the point about trying to find sort of like the smallest sort of unit that you can build like a function off of. So like, I think that's really important. First of all, is to like, if you're working with tracking data, find that one play that is just sort of like an example of what you want to work with, and then create a function that's going to work perfectly on that one play. Everything, when you're developing it, it's going to be really fast because the data is tiny, even though tracking data is pretty big in total. And then, once you've done that, then you can explore ways to like map, parallelize, etc. I think, that was always a big part of my process, is starting really small and then expanding from there.
Yeah. And I'm going to add on, that's a great point. I mean, I think, and one of the things I did there was sample 5 plays and run the function on them. And so as you build out, like, don't go to the full data set right away. Is you started with 1, then start with 5, and then like, as you get confidence that things are working, then you don't waste time trying to run on the whole thing and having it crash. I think that's super useful. I should take my own advice on that more.
Yeah, I mean, I always find like when you're writing functions, so like, think in units of like what you want to get done, and then build it up from there. That's kind of what you guys were saying there. But, see now. Curious about your learning process. The talks are tidy, but where did you learn? Did you learn base first and then move to tidy?
Yeah, so I guess I'll jump off and say that like I learned base R at school. And kind of use that, and then used Python a little bit and kind of went back and forth. And I think really only once I got into actually like doing a lot of sports research, like after graduation, like or even maybe my final year as well. I guess the point that I would make is it's like tidy principles and the tidyverse and stuff was not something that I learned at school. It was definitely something that, you know, I learned using a lot of online resources. And frankly, a lot of times it just came down to like even stuff like following people on Twitter and seeing, you know, whenever they shared their code on problems, even if it wasn't related to sports at all, I'd be like, oh, like, I don't know that function. What does it do? Or, oh, that's a really clever way of solving that problem that I've never seen before. And then like just sort of adding all of those things to my repertoire.
Yeah, I think Twitter is a great resource. For me, it started with, I had a friend, Forrest, who I got to work with at an internship, and he was all of a sudden, he's like, have you heard of this Hadley guy? And I was like, no. He's like, oh, he's the best. Like, everything needs to be tidy, blah, blah, blah. He's super stubborn about it, and like, kind of like convinced me that it was good, but I wasn't totally convinced. And then the next internship I did, I was super stubborn about it. I was just like, everything needs to be tidy. And so then instead of just taking the easy way out, you force yourself to search what is the tidy way to do this, and you start to learn about new functions and new packages that you didn't even know existed. But of course, Hadley's already thought of it, and it's like there for you, and everyone else who works on the tidyverse. But it's just like, oh, how do I tidily do this? And it's often there. And at that internship, I had a couple of people who were teaching themselves are just themselves. But you go through their code and there's like 3 different ways of creating a new function, because every time they forgot, they Googled it and got a new answer, and one's tidy, one's not, one's like, yeah, it's all a mishmash of things. And so I was super stubborn with them, like, choose one way to go. If you want to go base, go all base, but make sure you understand what you're doing rather than just grabbing stuff from Google. So for me, it just became like, how do I do this tidy? How do I do this dplyr? How do I do this tidyverse? And just forcing myself to learn those things, and now it's just natural and it comes quick.
There you go. Yeah, it's definitely a process. And I mean, I would say learning both is a great way, so you really understand what's going on with the R code, because tidy is fantastic. I love working in tidy, but it's not always the best way. Usually is, but not always. See now, what do you wish you could tell your younger selves when you were just getting started in sports data and data analytics, whether that's working with data, communication, or hopping into industry?
Wow.
So I guess I would tell myself, first of all, like, you're not gonna fucking believe what's about to happen, because like I, you know, did a bunch of public hockey research, then like worked in the NFL for 2 years, and then came to the NHL. So I'm mostly just like really thankful for that. I think, but what I would tell myself certainly is that, you know, one of the biggest things I learned while working at the Eagles that, you know, I want to continue to learn, you know, at the Kraken is really the importance of communication. I mean, you are going to, in sports, inevitably be talking to an audience and a lot of stakeholders that do not have the same background in stats that you do. And there is truly an art to being able to explain things like regressions and things like, you know, model estimates and model uncertainty in a way that's very, you know, understandable to the layman. And I say layman, but the truth is, especially when you're within a team, those people also have a lot of knowledge that you would benefit from listening to as well, because, you know, they're the experts in the sport, whether that was hockey now or football at my last team. So I think, you know, being super respectful of that and then finding ways to make your work as accessible as possible is really, really important for when you're working in sports and even publicly, right? Like, you know, if you're writing articles for people, you don't just want the only people to read those articles to be ones who are like super stat nerds. You know, you probably want to appeal to a wider audience than that. So it's just so important to try to communicate as simply and effectively as possible.
Yeah, I think for myself, I was trying to think when Namita was talking and I didn't call it anything great, but I think like patience and confidence, it took a while for me to learn, and it took, I want to say, like 4 years of just like slow, if not more at this point, 5 maybe, slow learning before like I got on anyone's radar before like anyone followed me on Twitter. Like it just took a while of me learning and honing my skills, and then but also so patience on that side of things, but also confidence in the work. I spent a long time again like just following and liking people's stuff and learning, and like I think I could have tried more sooner. I could have tried to put out a project or try to recreate somebody else's project, or just try to compliment somebody like by actually writing out words on Twitter before I did, and I think confidence was a big part of that. And I just kind of sat there and learned and read, and then I kind of went. So I don't think it went wrong by any means. I'm super lucky to be with the craft and everything's worked out well, so I can't complain too much. But I think patience and confidence to my younger self would be good.
Great answers. So I see a lot of detailed data from TV broadcasts tracking players' ball movement. How much of this data is available in hockey? Do arenas have multiple cameras for the purpose of collecting tracking?
So tracking data is kind of on the way to the NHL. So I think, obviously the pandemic has kind of thrown a wrench into some of the like specific schedules of everything, but I think in the near future, you're going to see more like tracking based statistics in hockey. I'm not sure the extent to which they eventually want to share that publicly, but we'll see what happens. And I'll just say, like, in the NFL, there's been a ton of really awesome research related to tracking data. The Big Data Bowl, as Dani mentioned, has been a really cool way to get the public involved with working with tracking data, and Next Gen Stats is building out a lot of models to share publicly. And then as well, teams are working with that internally as well. So I think, the NFL has been a really cool success story of tracking data so far, and there's a lot left to discover with it. So hopefully, hockey will experience some similar success as well.
Yeah, and if you check my slides, there's that link to the GitHub, or if you just go to the NFL's GitHub, I don't know exactly what it is. They have a sample game of tracking data, which again, the NBA took everything down. I'm pretty sure there's some lying around in GitHub's places, but there are samples out there that you can get your hands dirty with and just get experience with. So don't let the lack of availability in mass let it stop you from exploring it.
Awesome. I think we're going to do 2 more questions and then we'll call it, because it's been a long hour. So in your role, do you get to work with the physical performance teams who are working with the athlete, training load, data, etc.? If so, what can sports science learn from analytics then, and what can analytics learn from sports science?
This is a great question that we specifically are not well equipped to answer right now because we don't have players. I know Dani has done some public research on this, and I will say that certainly that was a data source that was available to us at the Eagles. It is a really interesting data source. What I think is tricky is that, especially like, let's say you're working with something like injuries. Injuries are a fairly rare event. They're hard to predict. There's not always a ton of signal, in what you're looking at. So I think, I would just say that it sounds bad, but almost, my advice would be to sort of lower expectations as to the nature of the predictiveness and the definitiveness of the answers that you expect there. But still, there's definitely some interesting insights to be found with that sort of data.
Yeah, no, for sure. And yeah, you alluded to some of the public. So I've worked as an RA for Eli Meiselman and worked with Aaron Pearson at SFU, who are physiology students, and their work is really cool. Not exactly injury, but kind of it's the sports science stuff is cool because you can ground it in physiological models that have been tested in labs and stuff, and you can do kind of more robust. There's more robust kind of randomized trials and stuff in physiology, and so there's a lot of theory you can borrow from. That's really cool. So I think that's a really nice side of the sports science side of things, and it makes it nice to work in. Although again, like Namita said, the injury side of things can be super tough, just because of the amount of signal you're going to find. But I think it's really cool work that you can do there.
Awesome. Alrighty. Last question. What is the best way to break into sports analytics? I'm practicing by writing fantasy football articles for 2 major sites over the last couple of years, and use R in my articles when possible. By break into, I meant professional team or league.
Well, I mean, I think, you know, the number one advice I always give is to put all your work out there publicly. You know, that both Dani and I do have like a resume of public research, which has helped a lot. Like I can say like at this point, like all the teams I've talked to in terms of working for them, you know, they don't even care about my degree anymore. Like they just want to hear about like the projects that I've done and how specifically those could help them. So, you know, maybe I would say if you specifically aspire to work for a team and you're putting out public work, maybe think about like what sort of application would be interesting to you and relevant to a team. So for me, I found that that was draft analytics. I found it to be a really interesting sort of like statistical and game theory problem to sort of figure out what's the best way to draft strategically and effectively, and that turned out to also be something that teams really were interested in, and not even teams in the sport that I originally did the research in. So that was cool. So yeah, I think, you know, if you're thinking about what are teams going to find interesting, the answer is certainly stuff like draft analytics, also like how to evaluate pro players, how to optimize performance on the ice and on the field, so more strategic recommendations on how teams should play, you know, which free agents to sign, like those sorts of questions. If you say something interesting about that online, I do think, you know, teams will notice.
Yeah, I mean, my first thing is like be absurdly lucky. And that's not super helpful. Like, things have gone right in my life, like not apart from like, you know, where I was born to like where like random twist of fate of where I went to school and like all sorts of things that have led me to like, you know, really good situations that have put me in spots to succeed. And I mean, there's the hard work and be good part of it, but like a lot of that is a lot of luck. But I mean, in terms of practical advice to use, I think Namita said it really well. And to add on, if you're going to put work out there, don't be afraid to recreate work that others have done. That's a great way to engage with somebody in a really natural way. I was always somebody who found it really weird reaching out to somebody cold, but if you kind of do a project and you do your own twist on it and you want feedback, like it's a great way to respond to somebody's work is to engage with it and do it yourself. So I think that's a cool thing to do. And again, like when you put stuff out there, you'll get you start to get noticed. The other thing is that a lucky part of myself, again, was that if you're in school right now, to look and take advantage of that. If there's a professor you can learn from that will supervise you, if there's a directed studies class you can take, if you can do a class project, if you can get funding to a conference, like there's a lot of things that school did for me that were super, super helpful in getting me kind of talking to people in the sports analytics world. And so that was super, super helpful. And so if you're in school right now, like really take full advantage of what it's offering. But hard work, putting stuff out there, and working on your communication skills, I think are the summarizes it pretty well.
Wow, super great answers. Thank you so much for answering those. Well, I think we're gonna call it